Hey there, ladies and gentlemen, boys and girls. Today we are going to talk about a little bit more about the nucleus, and we're going to talk about half-life. All right, just as a quick heads up, this topic is a little challenging conceptually. A lot of students really struggle with this one. All right, but it's actually really one of the more important ones because although it's very challenging, it's actually one of the ones that we use more often in our everyday lives. We take advantage of this idea of our understanding of what half-life is, and we use these different isotopes of atoms and knowing their half-lives for all kinds of different things, whether it's in the materials fields about building things and creating things, whether it's in types of metals. We use it in the medical field, especially a lot in the medical field. We use it for dating things, like in the fact of like how old something is. And so we're going to explain this little concept called half-life. All right, but before we're going to end by talking about half-life. We have to go way back here. We have to talk a little bit about the nucleus. All right, now remember, in the nucleus, right, where we have electrons on the outside of the atom, very, very deep down inside the atom, very, very small and very, very dense, is this nucleus. And in there are protons and neutrons. And remember, protons are positively charged, which means they want to repel each other. Two positive charges are going to want to repel each other. The only reason why they don't fall apart and repel each other is because there are neutrons there. Neutrons act as almost kind of like a glue or rubber bands to kind of hold those protons together, but you need to have the right amount of neutrons. All right? Not enough and the proton falls apart, or the protons overcome it and the atom falls apart. Actually, even too many neutrons is actually a problem too. All right, and there's reasons for that, deeper and deeper science there. All right, but we need to know that there's a certain amount of ratio that we need to have of the number of protons and neutrons. For some atoms, it's the same number. For bigger atoms, the more protons we have, we need even more neutrons just to kind of keep all those protons together. So you got to keep that in mind, that protons are always trying to kind of repel each other, but neutrons are keeping them together. And that brings us to this idea of stability, what we call nuclear stability. All right. So right now I have this picture of an atom here. This is 1, 2, 3 protons. That's lithium. It's got 1, 2, 3, 4, 5 neutrons. So that's lithium 8. Right. That one's pretty what we call stable because it's got a good number of neutrons to hold in those protons. All right. Now what I have right here is fluorine 18. All right, so this is an isotope or a version of fluorine. All right, this one has 9 protons and 9 neutrons. All right, but fluorine 18, all right, is unstable. All right, and by that, by unstable, it means that there's not enough neutrons to base it, the right number of neutrons to give that balance to be able to hold those protons together. And so anything that's not going to stay together is eventually going to fall apart, right? We use that unstable. If I said, okay, I want you to go up on that ladder, but be careful, that ladder's unstable, you're going to be like, ooh, that's not good because that ladder might fall apart. And it's kind of the same way here. This nucleus is eventually going to fall apart, but there's different levels. So it might fall apart right away. It might take some time, but either way, it's going to fall apart and it's going to try and become something much more stable. So oxygen 18 is stable. It has a good ratio of protons and neutrons. And so what some isotopes will do is they will basically will have the fluorine that's unstable and it will fall apart, break down, lose pieces of protons and neutrons, and it will become oxygen. In this case, it's actually going to lose a proton. All right, it's going to lose a proton, and that losing that proton changes the element from fluorine to oxygen. This process of breaking down is called decay. It just means to break down. All right? And anytime any isotope, unstable isotope decays and becomes stable, it releases energy. That released energy is called radiation. All right, that's what we feel of when we think like, ooh, isn't that really radioactive? All right, this is a radioactive isotope. All right, because it is unstable, it breaks down, releasing radiation, turning it into a stable atom. All right, so for example, all right, if I have, let's say, a sample, I have a fluorine 18 sample. One second. I want to give myself a little bit more space. Over here. All right, that is unstable. Let's say we're going to start with 20 grams of unstable fluorine. So I'd say I have a sample of fluorine 18 that is unstable, right? Which means, if it's 100% unstable at this point, right? Which means, I haven't had the chance for any of it to decay to become stable. So out of my 20 grams, right, I would also have my oxygen 18 sample. To start, I have 0 grams. All right. Now, one thing that we've noticed, all right, through scientific experimentation and some mathematical reasoning, all right, that when fluorine 18 exists, and let's say I have a sample here of 20 grams, it's pure fluorine 18, right? If you wait about 2 minutes, it's not very long, right? You wait about 2 minutes, you go wash your hands, right? And you come back. After 2 minutes, out of that 20 grams of fluorine 18, only 10 of it will be remaining. We only have 10 grams left now. And the question is, well, matter can't be created or destroyed. Where did it go? It decayed. After 2 minutes, half of the fluorine atoms have become oxygen 8 atoms. So they didn't disappear, but after that 2 minutes, 10 of the grams are now fluorine 18, but wrong color. 10 of the grams are now oxygen 18. So for example, if I had let's just say fluorine 18 is a gas, but let's just for the sake of this say I have a solid sample of fluorine here, right? Fluorine 18. Right? After 2 minutes, half of it is now fluorine 18, and half of it is oxygen 18. Right? Half of it has gone through this part. So now we are at 50, 50, 50. Right? But it doesn't just happen after one time. It seems to happen every 2 minutes. All right. So after another 2 minutes, well, it's not half of 20 because that's not how much is left. All I have left now is 10 grams. After 2 minutes, half those atoms of those fluorine atoms decay. So half of 10 becomes 5 grams. Right? And that extra 5 grams didn't disappear, right? They became stable. So all that's happened here is now a total of 4 minutes, after 2 minutes, it became half and half, right? But after 4 minutes, we literally took half of what was left and half of that. Right, so let's put it this way. We had 2 minutes. After 4 minutes total, all right, the majority of it now is oxygen 18, right? we can keep going. So after another 2 minutes, half of those remaining unstable isotopes will decay. .5 grams, which means this number keeps going up by half of what's left. Now we're at 17.5. Notice matter's not being created or destroyed. I had 20 grams. After 2 minutes, I still have 20 grams total, 20 grams total, 20 grams total. The only difference is now they are switching from unstable to stable. Each time it is releasing energy. So after another 2 minutes, half of what's left, after 6 minutes, all right? So after 6 minutes, very little of my original fluorine 18 sample is still around. It's decayed, right? And it decays by half every 2 minutes, right? This right here, this 2 minutes, how long it takes for half the atoms to decay. This is called half-life, right? All right, half-life. All right, besides being a great video game, for those who got that reference, all right, is the time for half the unstable atoms to decay. It's a measurement of time. In this case, fluorine 18 has a half-life of 2 minutes. Every 2 minutes, half of its atoms decay. Every isotope has a very specific half-life. For example, carbon-14, right, which is we find in our bones, actually has a half-life of about 5,730 years. Right? We use that and we know how long its half-life is to measure the dates of fossils we find, based on how much carbon-14 is remaining after a certain amount of time. Right? Uranium-235, right, which we think of when we think of nuclear power plants. Uranium-235 has a half-life of 4.5 billion years. That's how long it takes for half the atoms of it to decay. It's a very slow process. Some happen very quickly. There are some of the ones that we've created, those bottom ones on the periodic table, the ones that are man-made, their half-life is microseconds. Right? It takes less than a millionth of a second for them to fall apart. Right? And each step of the way, we're just getting less and less of them here. So in this case here, we start with 100% unstable. Then we are down to 50% unstable. Then to 25% unstable. And then down to 12.5% unstable. And we can keep going. But the amount of stable atoms increases because this is going down. These two numbers should always equal the total. Right? So I'm going to stop. I'm going to pause it right here. And I'm going to show you guys what it will look like, a little bit of a graph here. All right. Okay, so I'm going to use this really cool simulator here to really kind of gives you a showing of what's happening there in terms of how it looks like on a graph. Because a lot of times we interpret this data that we collect, because we can't see atoms, we use graphical data to do this. So I'm going to run the simulation once, all right, and just to kind of give you an idea what it looks like, and then we'll go back and kind of talk about, and then we'll do it again and talk about it. All right, so here we go. By the way, it makes kind of an annoying sound, just as a heads up. There we go. All right, so we start with a bunch of the red atoms down here. These were the radioactive or unstable ones. All right, and then it turned into these gray ones, which are what we sometimes call the daughter atoms, because they're kind of the result of it. These would be, in this case, the stable atoms. All right, and we started with 120 of them. all right? And so this is what we end up getting here. This is what we call in mathematics, this kind of curve here. This is what we call a decay curve, all right? And we use it for all kinds of stuff, not just because it's because it's slowly getting lower. It's not a straight line down. It's a curved graph. And you notice that it's getting, once it gets down to the bottom there, it's leveling off there. It's harder and harder to do those last few, right? So every time the red one turned into a gray one, you saw a little squiggly line come out. The squiggly line was showing energy being released, all right? So now if I wanted to determine, right, what the half-life of what this was here, we know we start with 120 atoms, or this could say 120 grams or 120 pounds, but we start with a certain amount. In this case, it's 120 atoms, all right? Nice thing is I can drag this here. After one half-life, half of that should be turned into stable daughter atoms. So if I start with 120 unstable, after one half-life, I should be down to 60. So I'm going to see there on my graph when that number goes down to 60. Oh, there we go. You see that T is equal to 31, or time is at 31 seconds. It took 31 seconds for half the atoms to decay. All right. So now if I'm down to 60, another half-life would bring me down to 30, which should be another 31 seconds. So I'm going to predict that it should be down at time is equal to 62 seconds. Let's check at 62 seconds. At 62 seconds, I should have half of 60. There we go. I'm at my second half-life here, or time is equal to 62 seconds. So in this case here, we have isotope A. Its half-life is 31 seconds. Every 31 seconds, so another 31 seconds would be, what, 93? Half of the remaining isotopes decay down to 15. All right, I don't know if it goes into decimals. All right, once you get into smaller numbers, it gets a little bit trickier because you can't have half of an atom. All right, so let's look at that. Let's try this again, but let's look at a different atom here. All right, and see how it compares. Let's do isotope B. All right, let's run it real quick and check its half-life. Starting with 120. This line's pretty steep. All right, but it's still got that decay curve. All right, so if I start with 120 to see how far, what its half-life is on a graph, I should see how long it took for it to become half. So we're starting at time equals 0, 120, that's our y-intercept there. How long does it take to get to 60? 17 seconds. So the half-life of isotope B is 17 seconds. Every 17 seconds, half of the atoms decay. So at 34, we should be down to 30 atoms. There we go. All right, so on and so forth. That's 2 half-lives. All right, if I go down to when there's 3, after 3 half-lives, gone to 120, down to 60, that's 1 half-life, down to 30, that's a second half-life, down to 15, that's a third half-life. 51 seconds have passed. All right. So that kind of shows that graphical representation of this. All right. It makes it a little bit tricky. It's just taking the time to be able to read some of these graphs. But that's going to do it for this video here on isotopes and half-life. This stuff can get a little tricky. Just take your time. Otherwise, good luck, and may the science be with you.